Hi folks, this is the solution to Wednesday, April 22nd's recitation. First question asks us to imagine a rod that is pinned down on one side and is falling under its own weight. So like any of these problems, we need to understand the torques that act on this object. So we'll draw an extended free body diagram. Um, there's a force here from the hinge. We don't really know which way it is. I'll just label that, and we can remember that its direction is unknown. But there is a force from gravity that acts downward at the center of mass of the object. Now, as this falls, so the part B asks us to find the torque. Well, let's start with part A. If the rod is falling, is the angular acceleration constant? No, it is not. You might imagine that if the rod is vertical, for instance, if it is here, then the angular acceleration would be very small because it's almost balanced. The torque due to gravity is very small. But if, as the rod falls lower and lower and lower, the torque is going to become larger and larger and larger until here, when it's horizontal, the torque will be at its largest because the force vector from gravity here will be perpendicular to the radius vector. So let's figure out how to calculate the torque as a function of angle. Now we know that torque, whoops, wrong tool. We know that the torque is the force of gravity times the perpendicular component of the radius. Well, the perpendicular component of the radius is this one, the one that I'm drawing in red right now. So that's our perpendicular. And a little bit of trigonometry shows that our perpendicular is L over 2 sine theta, because this distance is L over 2. So when the rod is horizontal, the torque is, so the force of gravity is just mg, so this is going to be mg times the cosine of 0 degrees, which is just 1, equals mg, which is 50 newtons, 5 kilograms times g. So mg here is 50 newtons. Oh, whoops, I forgot to multiply by the length. That's wrong. All of you about to throw things at me are completely right. This is mg times L over 2 cosine theta. Here theta is 0 degrees. So this is just going to be mg times L over 2. So that is 50 newtons times 1/2 meter, or 25 Newton meters. Again, note that this is equal to mg times L over 2 cosine theta. And we're just going to plug that in for all of these. I don't know the cosine of 10 degrees off the top of my head, so I have to ask Google. So this one is going to be mg times L over 2 cosine 10 degrees, which, putting in the numbers, is 24.6 Newton meters. Again, I'm just putting in the different numbers. Mg times L over 2 cosine 45 degrees. That's going to be 17.7 newtons. And finally, if it's vertical, This is going to be mg L over 2 cosine 90 degrees, which is 0, which is what you expect. If it's straight up, it's going to be balanced. So here, this is just a game in calculating torques. Calculate the perpendicular part of the radius, and you're good to go. As a reminder to everyone watching, there are 3 equivalent ways to find torque. Torque is equal to the force times the perpendicular part of the radius, what we just did, or the force perpendicular times the radius, often that's easier, or FR times the sine of the angle between them. Notice that this angle theta is not the theta we were given in the problem. That would be this angle here, the one that I just drew in green. So let's move on and apply this. A seesaw has a total length of 4 meters supported by a pivot at the midpoint. A child, mass 14 kilograms, sits on one end, a distance 2 meters from the pivot. Another child wants to sit somewhere on the other side. Okay, so doodle the seesaw if it is horizontal, showing all forces that act on it. Make sure the tail of each force vector begins where the force acts. So this is asking us to draw an extended free body diagram. So here is our seesaw. There's it. We have 2 children on it. So one of our children will be 2 meters from the pivot at the end. So here's one child. This is mass m1. The pivot is in the middle. We know this distance here is 2 meters. We know the other distance is 2 meters. Now there's another child somewhere else. We don't know where. We're going to wind up probably solving for that unknown distance, so we'll label this distance x, and we'll find it in a moment. Okay, now we need to label all of the forces. Well, there's a normal force going up from the pivot. We'll label this F sub n. There's the weight of the pink child over here, which is m2g. And the weight of the red child over here, which is m1g. There's also the weight of the seesaw, the weight of the thing itself. We don't even know its mass. So we'll just draw it here. Fg, I'm going to write S for seesaw. Now, the fact that let me draw one more thing. I just want to color in this wedge to indicate that it is the pivot. Now, we're choosing the pivot to analyze the torque, which means all of those forces that act at the pivot are going to have 0 torque at all. So we're going to choose the conventional coordinate system where counterclockwise is positive and clockwise is negative. So the only forces here that cause a torque about that pivot are the weight of the red child and the weight of the pink child. Red is on the left, pink is on the right, if anyone is colorblind. So I noticed that the radius vector is always perpendicular to the force vectors here. So this is a little right angle. So red child is going to apply a counterclockwise torque because his weight is trying to make the thing turn counterclockwise, and that's positive. I'm going to call this length L. Just because I don't like numbers. So the red child applies a torque of distance L over 2 times force m1g, and it is positive. Pink child applies a torque of x times m2g, because again, d2 is the distance. Sorry, we were told what variable to use. So rather than x, I ought to be using d2. That's what the problem tells me, although you can use anything you want, really. So that's the sum of the torques. So here is the sum of the torques. Now, for the angular acceleration, we actually don't know the moment of inertia of the board. So to find the angular acceleration, right, remember that the net torque is equal to I alpha, and the moment of inertia is going to be the moment of inertia of the red child, number 1, plus the moment of inertia of the pink child, number 2, plus the moment of inertia of the board, or of the seesaw, I'll use S, and we actually don't know that. It turns out that in part C, we're interested in the case where it doesn't accelerate, so it's not going to matter. But for this part, I need to write everything down. So the sum of the torques is going to be the torque from the red child, L over 2 m1g, minus the torque from the pink child, child number 2, d2 m2g. And then I need to equate that to moment of inertia times angular acceleration. Well, what's the moment of inertia? The moment of inertia of a single small object is mr squared. So this is going to be m1 L over 2 squared for the red child, plus m2 d2 squared for the pink child. And then the moment of inertia of a long object is 1/12 ml squared. So this is going to be 1/12 mass of the seesaw times its length squared. Again, I don't know that, but that's fine. Times alpha. Now, we are supposed to solve for alpha here, but I'm not going to do that. You can just divide both sides by that expression. It's not that interesting. Part C says solve for the distance d2 if the seesaw is not accelerating. So that means the whole right-hand side of this is 0. If alpha equals 0, then I have L over 2 m1g minus d2 m2g all equals 0. So that's a pretty easy game to solve for d2. D2 is L m1g over 2 m2g. And the g's will cancel. So that's pretty easy. Part D asks, if the child were at this distance where it's balanced, and then someone tilts the seesaw, would its angular acceleration still be 0? And here it's easier to argue in words than to do mathematics. The answer is yes, because if we were to tilt this by some angle, right, if this were tilted like so, sorry for the wavy lines, my stylus is out of calibration. Let's try to get this right. If this is tilted, the force vectors would be angled like this, and every calculation of torque would pick up a factor of the sine of that angle. But those factors of sine theta would cancel. Yes. Every torque would now pick up an extra factor of sine theta or of cosine theta, depending on which angle you're measuring, whether it's the angle with the vertical or the horizontal. But the idea that's important is that these factors would all cancel, and you'd be left with the same answer. So that's problem 2. This is a static equilibrium problem, a classic one, where the sum of the torques is equal to 0 because something is balanced, it doesn't move. Here is another one. We're using a rope to hold a trapdoor open connected with a hinge to the floor. So let's draw our extended free body diagram. We've got some force from the hinge. I don't know how big it is, but it's here. F hinge. We also have the weight from the trapdoor itself going down here. Let's see, the trapdoor's mass we will call M. So that's going to be mg. And the tension here, we are just pulling it with a force F. That's already labeled for us. We need to do a little bit of trigonometry. We'll just go ahead and label some angles. Let's get this force of the hinge out of the way. I know I'm going to choose my pivot at this location, so I don't need to think about it. So I can say the torque due to the hinge equals 0. We never need to think about that force in this problem. If we were asked about it, we would need to worry about it. So let's see. We know that the angle is 60 degrees with respect to the floor. So that is 60 degrees. So that means that this is also 60 degrees. And this little angle in here, that will be 30 degrees. I can do a better job of writing that. It'd be hard to erase. Okay. How much force should you pull with to keep the trapdoor at rest? So what I know here, at rest, the angular acceleration is 0, and thus that implies that the net torque is 0. So the torque from gravity is going to be negative because it goes clockwise, negative force of gravity, the perpendicular component times the radius vector. So the perpendicular component here is going to be mg times the sine of 30 degrees, or times the cosine of 60 degrees, however you want to think of it. So that's going to be minus mg sine 30 degrees, and the radius here is L over 2. The torque due to the force that you're pulling with, say rope, this is positive. F is the size of that force. We'll solve for it later. Its perpendicular component, right, if we want to think about that, that perpendicular component is going to be, let's see, this one. Oh, my program crashed. I'll be back in just one moment. Please stand by for just one sec. We are back. So we were calculating the perpendicular component of that force. That's this one. So this is F times the, let's see, if that angle is 60 here, whoops, I know I was confused. The perpendicular component, the one perpendicular to the rope, or to the radius vector, is this one. So F perpendicular equals, so that's 60. That means that this one is 60. That's F sine 60 degrees. So the tension in the rope then is going to be F sine 60 degrees times the radius vector, which is 3L over 4. So now we know those things add to 0. So that means we have minus mg L over 2 sine 30 degrees plus F sine, well, F times 3L over 4 sine 60 degrees all equals 0. Now we need to solve for F here. So here F will be, let's see, so the L's are going to cancel. So this gives me 1/2 mg sine 30 degrees, all divided by 3/4 sine 60 degrees. I do in fact know, well, I don't know its mass, do I? Oh, yes, I do. It's 10 kilograms. Derp. So I'm going to have to just type this into Google Calculator, right? I have 1/2 times 10 kilograms times 10 meters per second squared, that's g, times the sine of 30 degrees, divided by 3/4 times the sine of 60 degrees. And Google Calculator is thinking about this and telling me that this is 38.5 newtons. Okay, so now what if we pull a little bit harder? Well, if we pull a little bit harder, now the angular acceleration is not 0. Now I know that the net torque equals I alpha. So the net torque now is going to be minus mg L over 2 sine 30 degrees plus, I'm going to write this in a slightly different order, 3L over 4 F sine 60 degrees equals I alpha. Well, I for a board about its edge is 1/3 ml squared. So 1/3 mass of the board, length squared, times alpha. So that means that I need to get alpha by itself, I need to divide through by m, multiply by 3, and divide by L squared. So doing that arithmetic, that's going to get me alpha equals, so I'm just going to keep everything in one big fraction, minus mg times 1/2 sine 30 degrees. I know mathematicians usually don't write things in that order, but that's fine. Whoops, I forgot to multiply by 3. So that's times 3 over 2. Yeah, we will write it in the customary mathematician order, right? Oh, why is this crashing so often? I don't understand. I'll be right back. This program that I'm using here is still slightly beta software. So where were we? Let me erase this and start afresh. So we're solving the equation above for alpha. So we need to multiply by 3 and divide by ml squared. So this is going to give us minus 3 over 2 mg sine 30 degrees plus, and now let's see, I'm supposed to multiply by 3, so that gives me 9/4 f sine 60 degrees. And I'm dividing by a factor of L. And then all of this is divided by one more factor of L times m. So now I can type these things in to Google Calculator. So minus 3 over 2 times 10 kilograms times 10 meters per second squared times the sine of 30 degrees plus 9 over 4 times the force, which is 40 newtons, times the sine of 60 degrees. And then we want all of that divided by, so the length here is 1 meter. The mass was 10 kilograms, so divided by 10 kilograms times 1 meter. And when I put those numbers in, I get 0.29 radians per second. And that's pretty slow, right? But that's kind of what you expect because we're pulling with 40 newtons, but the force required to keep it balanced was 38.5 newtons. So it's almost balanced. And we're supposed to figure out whether it's opening or closing. So here this is a positive value, which means it's going counterclockwise, which is what we expect if we pull a little bit harder than the balancing value. So this is opening counterclockwise. So that was Wednesday's recitation.